Okay. The stream has begun, but really it's been going for like 40 minutes, just with royally messed up audio, which is a damn shame. Um, Mostly for me. I think it's like just nightmarish. But I'm going to try and just explain these pretty much. The good news is that the explanations should be pretty succinct and clear and not involve a lot of debugging or anything for the first couple problems that I already did. Um, in all my abstract computer science knowledge, um, I would do well to be a little bit more literate with OBS. But here we are. Okay, so string to integer, atoi. It's saying take a string and turn it into an integer. So the first thing is like find out if it has a plus or minus in front of it. If it does, get rid of it and record whether or not the number is negative. And then say, okay, just keep taking characters until we find a character that's not a digit. So for here, like keep going until we find that space. If we didn't find anything, return 0. If we did find something, turn it into a number. Make it be negative, it needs to be negative. If it needs to be negative. And then there's this rule about clamping it to the 32-bit signed integer range. So just say, like in Python, at least it's very simple. Like it's going to be the maximum of itself and negative 2 to the 31, and then the minimum of that and 2 to the 31 minus 1. So quite simple. This is actually, of all the meta questions thus far, the 51st most popular one has the lowest acceptance rate. Maybe there's something below that has a lower acceptance rate. I don't know. This is the one where I realized my audio was messed up, so I'll get back to that one. Word break. So this one's saying if you have a string and you have a word dict, can you reconstruct that string with all of these words? And the naive approach would be to say, okay, at every index, you don't even really need a cache, but at every index, if you've reached the end, then yes, you can construct S from those words. Or else try every word, see, like let's say at index 0, try code, that doesn't work, try leet, that does work. If that does work, you can move on and try the subsequent index. So then try leet and then try code, code does work, so then you move on and then you've reached the end. And the optimization is to say for this, every single time you compare, you have to so you're going through potentially all indices. You have to choose at every index between potentially all words. So you're already at 300,000 operations. And then for each one of those words, you have to compare every single character. So for leet and leet, you have to compare, like, is the L the same, is the E the same, and so on. And you can get around that with string hashing by just beforehand using a prefix hash for S. And for every other word, this is a fancy way of just hashing the word, pretty much. And then just saying, like, is the hash of this substring of S equal to the hash of this word? Yes. So it's very, very likely. There's a 1 in this chance that there's a collision, but otherwise it's overwhelmingly likely that this is the same as this, and you can move on. So that cuts back on the time complexity. And in theory, there could be a hash collision, but that's not really going to happen. Yeah, guys, and let me know if it's like a horrible audio nightmare right now and there's 2 of me arguing with myself, or if my voice is coming through clear. Like, please let me know. Okay, anyway, 2-sum. So there were 2 approaches to 2-sum that I unintelligibly went over. This is like a binary search thing. So it's like sort it, and then for every number, like here we are at 2. So if the target is 9, if you know that this is sorted, you can binary search and be like, well, what's 9 minus 2? 7. So just binary search and be like, is there a 7 in the array? Or if we use another example, like 3, here you'd be like, is there another 3 in the array? Yes. And actually, this exact test case means that you have to say binary search, but only after the given index. This is like kind of just a straight up suboptimal solution. The other solution that I at least visually went over was like a linear solution where you just say like scene is a dictionary for x in nums, if target minus x in scene, return, and we're returning the indices, so we're going to say for I comma x in enumerate nums, which means like for the index and the value in the array, return I scene at target minus x. And then in the end, we just say scene at x equals I. And then here, this should never happen. So we can say like assert 0. And this is linear time. So this does a lot better. And in my mind, this is easier to think about and less convoluted. Okay, this is where I got to before I realized the grave audio mistake that I have made. Okay, thank God. Oh, that is frustrating. But the good news of this moment is that I haven't actually seen this problem before. So, unlike these previous problems, this isn't really just me powering through explaining it. This is actually kind of my real-time analysis of what I would do and what I am doing to solve this. So the problem's saying you have this call stack, you have these different processes that have an ID. So like here, there's an ID of a 0, an ID of 1, and then they either start or end at a given time. So here we're saying like 0 starts at 0, and then 1 starts at 2, and then 1 ends at 5, and then 0 ends at 6. And my idea pretty much is have a stack and say like, record. It seems like we sort of have this situation where we have a stack, and we're only really, let's say like these are all the processes that are going on, or something like that. Let's say, oops, yeah, that. We only really care about whatever's at the top of the stack. So just like record the amount of time that something is at the top, either like with this situation until it gets popped off, or like this situation where it's at the top of the stack until something else kind of is then at the top of the stack. So here we would be like, okay, 0 has this much time at the top. ID 1 has this much time. ID 2 has this much time. 3 has this much time. Maybe ID 2 or 1 has like a tiny bit more time, and then ID 2 finishes it out. And this little thing that ID 0 has never actually makes it to the top of the stack. This seems like a bad call stack if something is getting added and removed from the stack without ever actually being accessed. I don't even know if that really abides by the logic of the problem, or if the problem can only have things end from the top of the stack. But either way, it doesn't. I think the situation I'm describing where this could start and end entirely not at the top of the stack. Well, actually, I guess what would happen is if it starts, it has to be up here. You could never have a case where something starts under something else. So really, it would have been that. And then really, this would have been up here. But either way, I'm not that worried about the logic. It's mostly just the implementation. Okay, so we got res, we got stack. Let's see. Yeah, what happens is there a world where 0 starts and then 1 starts and then 0 ends before 1 ends? That's actually sort of the one missing piece of information. Because if that's the case, then I think there needs to be another auxiliary data structure. The function whose ID is at the top of the stack is the current function being executed. Okay, 0 starts at 0. 0 starts at 2. Oh, there's just another instance of 0 going on. Okay. 0 ends at 5, 0 starts at 6, 0 ends at 6. That doesn't really answer the question I'm thinking about. 0 starts at 0, 0 starts at 2. 1 starts at 6, 1 ends at 6. And then 0 ends at 7. I think I'm going to modify this and see if it throws an error. So if I said right here, 0 starts at 0, 1 starts at 2, and then before 1 ends at 5, the first thing I want to check is what happens if we say 0 ends at 4? Does this throw an error that it's not sorted? No. So so I have to sort this because it's not guaranteed that it's sorted. And also, if this didn't throw an error, that also means that it's not guaranteed that something will end while at the top of the stack, which I would normally think for a call stack would be the logic. Like, it doesn't seem all that common of an occurrence for something to be added to the call stack and then concluded from the call stack without being currently running. That seems like, right? Like, usually it's like, okay, define this method, something's going to call this method, it's going to go and it's going to return something. But it's weird to be like, call this method, this will call something else, and then also remove itself from the call stack while that other thing is going on. That logic seems odd to me that could happen here, but that seems like a generalization that's not really that hard to deal with. But I think it does mean we need another data structure. We need something that's like, how would you handle that? I'll think on that while I'm implementing everything. Because I feel like a simple solution would be to have some sort of set or counter or something that's like 0 starts at 0, 1 starts at 2. I'm going to move this over for the purposes of like visualizing it slightly easier. 0 ends at 4, and then 1 ends at 5. You would want a way to remove 0 from the call stack effectively while 1 is still at the top. And you don't want to have to pop everything off, remove the 0, and add everything back on, because it's like an O of n operation. And my first thought is like have a set where you just say like, is 0 currently running? We would have something that's like running equals set. And then when 0 ends at 4, we would say remove 0 from running. But the problem is that there can be multiple instances of 0 running. I guess it doesn't really matter which instance of 0 ended. Actually, that's kind of intrinsic to the conceit of the problem. Like right here, 0 starts at 0 and starts at 2. When it then says 0 ends at 5, it's not specifying which 0 thread ended at 5, just like one of them ended at 5. So actually, I think you could use a counter for this. You could say like how many instances are running. If at least one instance is still running, right? Does that? I don't actually know about that. Because if you, let's say there's like 2 processes. And you said we have 0 and we have 1. 0 starts at 0, and then let's say also 0 starts at 1, and then we say, okay, those keep going, and then 1 starts at 3 and goes, and then let's say 0 ends at, this is tough. Let's say we had something that's like 0 starts at 0, 0 starts at 1, 1 starts at 3, another 0 starts at 4, and then if we said 0 ends at 7, let's say, or 0 ends at 9, how do we know which 0 is ending? To me, again, it's like logically, like understanding a bit about call stacks, it seems like the top 0 would always be the one that's ending. It would never be one of these, but if these are still running, is there any specification in this problem that those are the ones that end. I think the problem will have multiple solutions if it's not this top thing that ends. Yeah, I put Leo as an icon. It got him kind of close. It made me a little bit more into an anime character than, well, I'd love to be an anime character. But it made Leo pretty accurately, honestly. If a function is called twice, one call executing for 2 time... Okay, that makes sense. Means a function call with function ID ended at the end of timestamp 2. A function can be called recursively. That's fine. The function whose ID is at the top of the stack is the function currently being executed. It doesn't seem to specify. It doesn't seem to specify if here this would look something like 0 starts at 0. And then 0 starts at 1. I'm not gonna write start. 0 starts at 0, 0 starts at 1, 1 starts at 3, 0 starts at 4, and then 0 ends at 8. Like, I think there has to be specificity, because here the answer straight up changes. If this ended at 8, that doesn't affect anything, or that will affect something potentially later. Whereas if this ends at 8, that immediately has an effect. So like there's 2 different outcomes depending on which 0 process ended. Maybe in the constraints it says that. No 2 start events will happen at the same timestamp. No 2 end events will happen at the same timestamp. Each function has an end log for each start log. I feel like that specifically doesn't explain that. I'm just going to assume it works like a normal call stack. Which actually means I don't even think the counter would be necessary, because the counter will only matter if there were multiple competing instances of the same thread that were at different levels. Because the moment they're on the same level, it doesn't matter at all. But if there's like another thread sandwiched in between, it starts to matter. So I'll get rid of that. And this seems like mostly a pre-processing problem. So I'll say for I word in enumerate logs. It's going to be something like logs that I equals something. I think I'm going to say split equals word dot split colon. So now, assuming they don't do any BS, we should get a 0, a something, and then a 0. So I'll say log equals that. Logs that I equals log. Int SPL 0. Okay, and then if SPL 1 equals start, then do something. Or else, yeah, then I'll say log.append 1, else log.append -1, because I'm sort of envisioning doing some kind of a sweep line adjacent algorithm here. This seems not really like a sweep line thing, but that notation of 1 and -1 might come in useful. Or else I could just say log.append SPL at 1 equals start. And then log.append int SPL at at 2, I guess, just for the sake of consistency. Print logs. All right, let's see if this just like doesn't throw an error at least. Okay, cool. So now it's like 0, 1, 0. 0 starts at 2, 0 ends at 4, 1 ends at 5. Okay, yeah. So now I'm just going to have like for log and logs. I think I need like a previous time. I can just calculate that on the fly. So I'll say if stack, that means that you're about to add something to the stack and something else is about to be booted off the stack. Well, that's only if match. I think I do want log to just be 1 if it's start and 0 if it's not. So it's just going to be that now. Instead of 1 and -1, it's just 1 and 0. Okay. So for log and logs, if log at 1, then that means that we're adding this to the stack. So we have to do something. Or else, I guess what we're going to add to the stack is the ID of the thread and the timestamp at which that happened. So I think I'm just going to like write that all out. So ID X, or does a capital ID work? Yeah. I'll say type and timestamp equals log. So if type, that means that something started or else something's ended. Okay, and I'm going with the assumption that if something ends, that it was always at the top of the stack. Because I think if that's not the case, if that constraint isn't implied, which it's not explicitly stated from anything that I see here, if that's not implicitly true, then this problem kind of just has multiple competing solutions. So at the very least, it's a matter of interpretation, and I'm going to go with that interpretation. Which means that right here we know that if something ended, that then that ID is the current top of the stack. I think that makes sense. So that means that actually, and that means all we really need to store in the stack is just timestamps, because then the only time we will ever access. No, we still need it to have the ID, because like when we add something to the stack, we need to look at what was previously on the stack. We need to look at that ID. So here I'll say blank prev timestamp equals stack dot pop, because we're popping it from the stack if it's being removed. And then just like res at ID plus equals timestamp minus prev timestamp. Okay, that part's done. So here now, prev ID equals prev timestamp. Or no, what am I doing? Prev ID, prev timestamp equals stack at -1. Okay, and then it's pretty much just the same, like res at prev ID plus equals that. And then here we then say stack dot append ID timestamp. Okay, how does this do? Oh. Okay, this is actually a really good sign. I think this is a terribly written problem at this point, but the fact that the expected output is just blank tells me that actually in the constraints, what I was testing for earlier is true, that this is invalid, and you can't pop something from not the top of the stack, even though that's not explicitly said here. Which is good. So I'll reset the test cases and then go from there. That means that probably this will work and there's not another interpretation. Okay, this gives 3 and 4. No, this gives 8 and 3. How's it getting 8? It's probably getting... Oh, it's getting 8 because when this ends, it doesn't actually... It's seeing the beginning of the stack. Still, that timestamp is 0. So I think what needs to happen is when you pop something from the stack, then you say if stack at -1 at 0 equals, or stack at -1 at 1 equals timestamp. So say like, and now sort of actually the previous timestamp for say thread 0 is at 5. I guess maybe it would be timestamp -1. Or no, this wouldn't be timestamp -1. This would be, we're saying res ID plus equals timestamp, so that would be 5 minus the previous timestamp, which is 2. But really it should be +1 minus that, because you are starting at the beginning of 2, not at the end of 2. And here you're ending it at the end of the current timestamp, not the beginning of the current timestamp. Whew. I'm half expecting there to just be a lot more corner cases I'm not thinking about. Hopefully the string parsing is not a part of those corner cases. Or there's just no corner cases. Oh, man. Okay, so that's 4 done. Binary search tree iterator. Pointer should be initialized to a non-existent smaller number than any element in the binary search tree. Has next returns true if there exists a number in the traversal to the right of the pointer, otherwise returns false. Moves the pointer to the right, then returns the number of the pointer. Okay, so you're kind of just flattening a binary tree. I feel like that's what they're telling you to do here. Because, I mean, notice that by initializing the pointer to a non-existent smallest number, the first call to next will return the smallest element. So the idea is you return next, and it gives like 3, and then 7, and then 9, and then 15, and then 20, like in ascending order. And normally, my immediate monstrous instinct to flatten this into a list is curbed by the idea that an interviewer would hate that, because that's clearly against the spirit. And usually that's shown when, for like linked list questions or binary tree questions, they ask you to do it in O of 1 space. But here, has next. I'll try and think a little bit about how to do that in O of 1 space, but I don't think, like, I think the best you could do is have a stack and say, like, it would be a path from the root to the rightmost element, and then you would like pop and push and pop and push, and then eventually the stack would be pointing to the leftmost element at the end. But that's still O of n. Like, it's O of the height of the tree, so in practice it's probably O of log n space. Oh yeah, here we go. And use O of h memory, where h is the height of the tree. I guess I can do that. That's more interesting than flattening the tree. So I'll say stack equals that, self.stack equals that, while, actually, self.stack equals root. It's going to contain the root. While self.stack at -1, while the last thing in the stack has a left node, self.stack.append, self.stack at -1 dot left. So now we're going to have a stack pathing all the way to the left. Let's see, and the goal is O of h memory. So for next, For has next, are all the elements unique? No. Let's see. I could think of a way to do this where you just like destroy the tree as you go. I know, just flattening it. I keep making myself do it the hard way for these problems, which is good because I don't know how many people are really care about like doing it the greedy wrong way. But I guess I don't know. I guess I haven't done this the right way. So you have the stack. I'm thinking, when do you differentiate between? Oh no, no. I think I'm making this out to be more difficult than it is. I think has next will fall into places as it goes. But for next, you're gonna say the result is just gonna be stack at -1. It's gonna be the final thing in the stack. .val return res. I'm gonna do that so it doesn't have to like look in the outside scope every time. I guess that's not really what's going on there. But we're just gonna record, okay, a 3 is gonna be the first thing there. And then the hard part is like, okay, you're gonna pop the 3, and then what? I mean, the very next thing is going to be a 7. So you're just going to pop the 3, and I think you're done. So I think we'll say x equals, or no, I'll say stack.pop. So now it has a 7 and nothing else. And then if stack dot I gotta watch out because these, you could have multiple of the same element in a row. So I'm gonna say res is actually just stack at -1, and then this is gonna return res.val. But I'm gonna say if stack at -1 left equals res, that means we just popped the left element. And now you don't do anything. Now you're just done. And if you just, I don't think there's a world actually where you pop an element. I think I need another class variable for this. Hey. Because I think you want to see what was the last thing I popped the last time next was called. For example, if you're at 7, you don't want to always pop 7 because that's the root of the whole tree. You want to say, was the last thing I called this dot left? And if it was this dot left, then I keep this. But if the last thing I called was this dot right, for example, 15, then I would pop this as well. I kind of just want to do the flatten a list thing. After the audio difficulties, I don't know. I'm going to do that, and then if anything leaps out to me about this logic, I'll come back to this. So I'll just say self.list is this. Def df. No, is this? Yeah, I'm gonna do this. Node self.list.append node. Okay, the list has been flattened. I just couldn't resist. True. Yeah, that is actually terrible for him. Okay, that looks good. Res equals self.l at self.idx. Oh, I never called the FS. Okay. All right, I just had to get that out of my system. That one had to happen. Yeah. No, I think that's against the spirit here. Okay, but going back to the previous concept. So you're going to have a stack. I think that's all you really need. I guess you need like self.prev equals none. I think that's going to come in handy. I'm going to only define stack as self.stack, because if I say prev equals self.prev right there, I'm going to have to define this later. Like, I'm going to have something that's like prev equals res, but I really want to not make the mistake of just saying prev equals res. I want to say like self.prev equals res. It's going to look something like that at the end of the code. I think has next. If I play my cards right, I think this might just be return bool self.stack. That may well be what that turns into. Yeah, no, you joined after Jai, but yeah, it specifies that down below. But I was like, I really wanted to get the flat and the tree thing out of the way. So it's going to be a path leading to the 3. The stack is going to be 7, 3. I think what makes sense is to have the stack be 7, 3, and then 7 alone, and then 7, 15, 9, and then 7, 15, and then 7, 15, 20. Or, I don't even think you need to do that. I think 7, 3, and then 7, and then you pop the 7 and say 15, 9, and then 15, and then you would pop the 15 and say 20. Yeah, which means that if you called next while the stack was just 20, you would pop the 20 from the stack and the stack would be empty. So then this would be the correct evaluation. So with that in mind, then the question becomes like, how do you know when to pop something? So for 7, 3, it's like, do we pop the 3 or would it maybe have children? Or like for 7, like, do we pop that or would it maybe have had children? And I think we say if self.prev is the last thing in the stack's right child. No, I don't even think you need to say that. You say if self.prev is the okay. If self.prev is the current thing's left child, so let's say you've just popped the 3, Prev is 3. You're at the 7. I think that might be overthinking it. I don't even think you need a self.prev. I think you would just say if you're at the 7, pop it. Well, this specific case doesn't encounter this, but like I feel like there's a larger tree where the question is like, do you add the right tree? No, it's still fine. I think you always do the same thing. You say here we're just gonna say like while self.stack at -1.left, self.stack.append, self.stack at -1.left. So now stack should have 7 and 3. And then here, I think you just say res is self.stack.pop if res dot right. That means that this, like for the 7, if we popped the 7, we want to add the 15 and the 9. So we'll say inord, the in-order successor of this is res dot right, while inord is inord dot left, stack dot append inord. So I think what should happen then is when you pop the 7, you automatically add the 15 and the 9. And you never need to go back to the 7 because you've exhausted both of its children. And I think if there was something above the 7, you would like go through all this, you would go to the 20, you would pop that, and then there would be something up above on the stack, and then you would go from there. One test case. I guess I'll just go for it. All right, wasn't too bad. Random pick index 1. Given an integer array nums with possible duplicates, randomly output the index of a given target number. You can assume that the given target number must exist in the array. So we pick a random index. Oh, okay. Where nums at I equals target. If there's multiple valid indices, pick one at random. Okay. I feel like we just bucket them. So here, like 1, 2, 3, 3, 3, we're like, okay, there's only a 0 index for the element 1. There's only a 1 index for the element 2. For the element 3, there's 2, 3, and 4. Yeah, so I'll just say default tick list for I, x in enumerate nums. Self.bucket x.append I. And then here, I feel like all we really have to do is just say return random dot choice. I think it's random dot choice self.bucket at target. Maybe there's like a follow-up or something. No. I guess bucketing is kind of a novel concept. Given a list of accounts for each... Oh boy. Alright, well, spoiler alert, it looks like it's union find. There's a list of strings where the first element accounts that I at 0 is a name and the rest of the elements are emails. We would like to merge these accounts. 2 accounts definitely belong to the same person if there is some common email to both accounts. Note that even if 2 accounts have the same name, they may belong to different people, as people could have the same name. A person can have any number of accounts initially, but all of their accounts definitely have the same name. Their accounts definitely have the same name. After merging the accounts, return the accounts in the following format. The first element of each account is the name, and the rest of the elements of the emails. Okay. So here we would add John00 Gmail in. That doesn't seem too bad. That doesn't seem like the worst. Accounts at i.length is only 10. So I feel like what we do is we just have a disjoint set, and we say for every single account, ignore the name for now, and say take this first email, run union with that and every other email in the account. Say these are all now marked as having the same account person. And then do that again here. Suddenly, the moment that this union operation goes through, John Smith, John New York, and John00 at gmail.com or at mail.com all would be under the same name. And then in the end, you would just be like, once you have that information, I feel like it's not that hard. You'd say, look at the name. I guess you would just say, like, look at John, look at this email, add every single account that has this email, and then go account by account. So be like, here, have we seen these emails before? Mary, have we seen these? No. Like this John, have we seen this before? No. Okay. Root and size equals root is list range n, 1 times n. Message retracted. Did you guys break the... I should change the title of the stream. I don't think non-fucked audio is a very good name for a title. But I'll probably change that after because it doesn't really matter. Okay, root is that. Def find a. Okay, so those definitions are done. I actually need to define n, which is non-trivial, because that's the number of distinct emails. So I guess it's probably easier. How do I want to do that? I think what I'm going to do, I'm going to like not deal with that right now. I'm just going to say this is going to be a dictionary, and this is also going to be a dictionary because I'm dealing with strings and trying to arrange these in a way that like this is indexed. Like this is index 0 and this is index 1 and this is index 0 again. Like that logic is just going to be more difficult than actually just the rest of the logic. For account in accounts, for I in range 1, length of account. Oh, thanks. Yeah, not the greatest name for I mean, a lot of this honestly is just like I don't know, it's fun to explain stuff to people or like do this openly. But a lot of it also is just like, I guess, to put as a project on a resume. So I'll probably change the title before then, before I link this. Although it's actually already linked. Okay, so for each of these, for I in range length 1 and length of account, so there's going to be some email address at this index. I don't think the name matters here at all. I think that's sort of after the fact. In fact, I don't even think we need to look at the first email. All we really need to do is say union account at 1 and account at I. Okay, so now all accounts are linked, essentially. And I actually just want to check to see if this is like not gonna bring issues. Key error. Oh, oops. Okay, so here, that means I need to initialize these. So I need to say like, if account at 1 not in root, root at account at 1. How long can these email addresses be? Not long, so I don't really care. Equals account at 1. Size at account at 1 equals 1. Oh, and then I do the same thing here. Okay, so the logic checks out. Now everything's linked. I just have to like collect them all. So I think I'm just gonna have, I can't have a dictionary because there could be different Johns. I guess I know that the name associated with a certain disjoint set is gonna be the root. How can I actually get that information? I think I just go down the list and I would say, we have John, look at the very first email, look at the root of that, the flag node, find every email with that flag node. I guess that makes sense. I guess I just need like a scene set. So for account in accounts, I also need like a result. If, do these have a minimum length? Yeah, they have to at least have one email account in them. So I can say if find account at 1, if the first email's flag node in scene, continue, or else current equals that. Node equals this. Okay, and then I think I'm just going to iterate over all accounts. I think that's kind of fine. Is that, or I can iterate over all emails. That's what I can do. For email in, and there's one more optimization I can do after this, but for email in root, I think I'm going to say, yeah, this is fine. For email in root, cur.append email, but only if find email equals node. Okay, and then in the end, we're just going to say res.append account at 0, the name plus the list of all the emails. And then the last thing I can do to speed this up a little bit, well, I just want to see if this works. Return res. I think it should just be fine. I think the syntax is fine. Okay, John Smith at all these. So John is correct. Oh, and then it just goes again. I say if node in scene. So it's clearly the second account where it just runs again. And then Mary is correct. Oh, it's because I never add anything to scene. So I'll just say like scene.add node. Okay. John has John Smith at mail.com. John in New York. Oh, they're supposed to be like alphabetical or any. Yeah, in sorted order. So I guess it counts as 0 plus sorted cur. Okay. There's one more thing I can do to speed this up, which is actually not having a scene set, but instead saying if account at 1 in root at all, or I guess if account at 1 not in root, continue. And then right here for everything in cur, just remove it from root, which actually is going to speed up this operation for every subsequent like linked account. I think that should just be kind of parallel logic. For email in cur, root dot pop email. I think that's roughly equivalent. You're just checking that something's outside of a dictionary rather than checking if it's inside of a set. David5m.co. Oh, is there something about like not that even if two one 5 5 0 right here. So 5 and 0 should be linked properly, but they're not for some reason. So 0 is linked, 4 is linked, 3 is linked, 5 is linked to itself. And then 1 is linked to itself. But also other things are linked to 1. In fact, everything else is linked to 1. Well, interesting. This said, oh no, that's just for the other test cases. So I'll get rid of these other test cases for now. Oh, it's that I didn't include this if statement. So it's just recreating a root for a given thing every single time. Oh, man. All right, not too bad. I'm seeing strings and email addresses. That's always a pretty scary sign, but that wasn't the worst. Given an array of positive integers sorted in strictly increasing order in an integer k, return the kth positive integer that is missing from this array. I think this is like a pigeonhole principle problem. That's what this feels like to me. Because yeah, I mean, like you could have a heap or can you solve this problem in less than O of n complexity? I gotta go start my dog's dinner. Give me like 30 seconds. Okay, return the kth missing positive integer that is missing from this array. Oh, I see. So it's asking like 2 and 3 are there. Can you solve this in less than O of n complexity? Okay, I don't think this is a pigeonhole principle thing. Or no, actually I bet it is, because it's already sorted. I was thinking maybe it's not, because you would have to sort it to do that. Oh, no. This is the binary search thing. This, you look through the array, and you're like, if, say, 2 is at index 0, you know there's a 1 missing. If 4 is at index 2, you know that there's just one thing missing before that. So you just binary search through until you find like the number of things missing before that. So we'll say like, I feel like, do I want to use bisect left for this? I think that's, do I want to do that? Yeah. I think it'll get kind of gross and unreadable, but it's worth at least like attempting because it's kind of fun. Return, so it's going to be bisect left, and then I think it's not going to be one of the element. No, this is going to get really ugly. I'm going to say L and R equals 0, and then worst case, I guess the array is empty and K is 1,000. So worst possible case, the kth missing positive integer is what, K itself? I'm just going to say 1,000 right now. While R minus L is greater than 1, something, and then in the end it's going to be I think we're going to return L. I bet there's a way to phrase this where you could do either of them, but it's going to be like evaluate a number of 3, and then how many missing numbers are below that, aka how does this match up to its index. So I'll write like a separate check function just to keep it cleaner, I guess. Def check m equals L plus that over 2 if check m. If check m, that means that there's at least k missing numbers below that. I think that's the wrong way to think about it. I think you're going to select a kth missing number and then say there are at least that many numbers in the array. So I think there might actually be 2 nested binary searches here. But what M is going to be is it's going to be like missing number guess. So the kth missing number can be anywhere between 0 and I guess k plus 1. So if check m, L equals m, or else R equals m. And then what M is going to be is like if there are at least, how would you phrase this? You're taking a guess at a missing number. So you would say guess 5. You would say there's 3 numbers in the array below 5. So you know that there's 2 missing numbers at 5. So you would say if there's too few missing numbers, L moves to M. It's going to be something like that. Oops. Oh wait, no, it's totally not going to be L and R 0 and K plus 1. R, we'll just set R to like 10,000 and deal with that later because it doesn't really matter what the upper bound is. 1 second. Go lay down. Good boy. Go lay down. Okay, L and R, 0 and 100. So M, we're going to say IDX equals bisect left, R, and M. Losing my marbles a little bit. So it's going to be... Go lay down. You're okay, come here. Up. Let's go. Good boy. There you go. Okay, so IDX is the number. Let's say M is 7. IDX would be 3. This is tough because, like, what if the numbers weren't sparse? Like, what if M was 3? That's okay. You would... Then it would be a tiebreaker. You're saying, ideally what you want is you guess 9, and you say, bisect left of this is 4. Or rather, the nearest element that's greater than or equal to this is 11. And 11 minus the number of elements below it, 4, is... So like R at I minus I is 6. So then you would decrement by 2. Except you can't decrement by 2. It's a binary search. But do you say bisect left or do you say bisect right? You say bisect left. And then you would say val equals, or num missing equals R at IDX minus IDX. Print num missing, and then it's ultimately just going to be something like return num missing is less than or equal to K. But there's going to be some caveats, because if you guessed exactly a number that's in the array, then that kind of changes things. But I want to see what this comes up with. Okay, R at IDX minus IDX if IDX is less than the length of array, or else every single number is less than this. So then you would just say like M, would it be M minus length of IDX? 1 second. I just want to even get this returning something that makes sense. Oh my god, I'm really losing my marbles. Length of array. Okay, and I'll make this be something more reasonable, like 20. Return the kth positive integer that is missing from this array. So we're saying with 10, there are 7 numbers missing, which I think is wrong, because we have 1, 5, 8, 9, 10, and 6. So it's overestimated by 1. With 5, it's saying there's 4 numbers missing, which I think is wrong. I think there's only 2. With 7, it's saying there's 4. With 8, it's saying there's 7. Okay, so I think it's like there's definitely issues with the logic here. Num missing equals, I think it's not r at idx. I think that's like severely misguided. I think it's just m minus idx, which actually eliminates that too. Well, if this precludes me having to think about this problem more, then I'm pretty on board for that. I was kind of under the impression I was in the initial stages of scoping this out, because this is, at the end of the day, like a nested binary search within a binary search. And I assumed there would be a lot of off by 1 errors, but the reason I hate binary search. I think the only thing I need to do is just be like, make sure this is big enough. Because like that can be whatever I want it to be. That can have a bajillion zeros behind it. This is one nice thing about certain binary searches, is like, as long as the bounds aren't too small, if they're too large, it doesn't really matter. I'm gonna just YOLO it. I bet there's some bullshit test case. There is not some bullshit, some BS test case, I'll say politely. Okay, 2 more to go. First and last position of element in sorted array. Not bad at all. Algorithm that runs in log n. So they just want you to do bisect left and bisect right. So 3 and 4 for target 8. So I think we can just do this in like a one-liner. So it's just going to be nums dot, or bisect left, nums target, and then bisect right, nums target minus 1. If target in nums, else -1, -1. All right. See, that one was a simpler binary search. None of this 2D nonsense. That last problem actually was pretty interesting. That's just, I think anything that's marked as an easy with a follow-up, I find extremely disorienting. Rotate, remove nth node from end of list. Okay. And return its head. I got 2 ways I'm thinking about doing this. The first way is like what I would do when left to my own devices, which is to say sent equals list node, next equals head. I feel like a secret to these is always like, the real secret is just turn this into a regular list, but the secret is like, just have a sentinel node pointing to the head, because 90% of your problems come from what if they deleted the head. That's like always the issue. And then length equals 0, scout equals sent, while scout dot next, or I'll just say while scout. N plus equals 1, scout equals scout dot next. Okay, so now we have, oh no, it can't be n. I'll say length, that's fine. Let me get your left and right pointers quick. Wait, what do you mean? Like for that Kth missing this one? The only thing you really care about is like if you're returning L, uh, you want it to be the lowest element that the answer could conceivably be, and if you're returning R, you want it to be the highest element the answer could conceivably be. And also, if you're returning L, you want R to be at least one larger than the largest thing it could conceivably be. And if you were returning R, you would want L to be -1. You would want it to be one lower than the lowest thing it could conceivably be. Okay, but anyway, scout out the population. And then it's just going to be something like scout equals sent for blank in range L minus N. 1 second, my water's boiling. My dog's getting that feast. For blank in range L minus N, scout equals scout.next. And then in the end, scout.next equals scout.next.next, and then return sent.next. So this should work even if you're deleting the head. And I don't really want to mess around with linked list problems right now, but like I feel like a lot of it comes down to just like remembering that a number is O of 1. You can always have as many numbers as you want, and you're going to have to iterate through the list anyway. So this O of n while loop, that's fine. So just like with linked list problems, if you err on the side of like too much with extra auxiliary numbers and statistics about whatever you're working on, that's going to work in your favor compared to if you tried to do this without. I feel like there's a world where someone subconsciously is like, do I try and count the number of nodes? No, that's too complicated, but it's not too complicated. I think if you didn't want to count the number of nodes, you could still do it. I think what you would do is have a fast and slow pointer, and you would say like, fast is fast.next.next, slow is slow.next, but only do that n times. And then once you've done that n times, then both of them are themselves.next, so that you've spaced them out by n. Yeah. In fact, I don't even think you need to do the .next.next. You would just have one have a head start by n, and the other one be behind by n. I like binary search. I guess this problem, I think it's just that it's deceptively hard. Like a 2D binary search, you don't see that every day. That's pretty whack. But like the problem after that, for example, what was it? Not accounts merge. This problem is good for like really concrete binary search fundamentals, because it's literally asking you like, do a binary search for the first index of that element and do a binary search for the last index of that element, and like being able to differentiate between those two things and just do both of them independently, I think is a really useful learning exercise. And it does feel really good to know the difference between what the hell binary search templates are, like what bisect left is and what bisect right is. Oh wait, that's weird. This says remove nth node from list, but then this says rotate list. But then when I click on it, it's remove nth node from end of list again. I think, yeah, actually the two cursors, I think that's probably clearer. And in my experience too, just like flattening, a lot of these problems can be solved if you kind of pre-compute. And I think that's better programming form. So unlike flattening a binary tree, I'm much more comfortable, even in a job interview setting, saying maybe they want me to do something without finding the count, but this is just better. This is better practice in my mind. But even still, it's a little. I feel like it's a little bit fun to theorize about how you would do it without having to do that. So I guess you could say like lim equals cent for blank in range n. Lim equals lim dot next. I think n has to at least be, yeah, n is at most the size. And then you would say, let's just say like node equals cent for, I think you would just say while lim equals lim dot next, node equals node dot next, node dot next equals node dot next dot next, return cent dot next. There's probably an off by one in here, but yeah, I think maybe I went one too far. So while lim, I think lim needs to be head actually. Yeah, like in example 0, where if you're deleting the head and there's nothing else. There it is. Oh, man. Are you guys applying to places right now? Oh, that's cool. What level are you applying for? Damn. Nice. Have you been studying a lot for it? Thank you. I know I tend to trip over my own words and I guess invite my clone into the room a little bit often, but I'm slowly getting the hang of streaming. And it's honestly the biggest utility is like getting good at doing these while someone's watching me. Because like doing these during a contest, I'm already pretty good at doing them under pressure, but at least for me, it's a different kind of pressure to have someone like specifically looking at you and having to explain everything out loud. Yeah, thanks for tuning in and always being encouraging. It's very cool of you. All right, I'm gonna go feed my dog.